All right, so we figured out Stokes' theorem that the integral around the boundary of a surface of a vector field is equal to the integral over the surface itself of the curl of that vector field, where we have compatible orientations. So let's do an example of how we can use Stokes' theorem to make our lives a little easier, or at least to give ourselves options. So let's imagine finding the flow of this vector field around this triangle here. It's part of a plane, but it's angled up a little bit. So if it's oriented counterclockwise from above, that means that we're going right this way. And if you sort of do your right hand rule, you'll see that we need to be orienting the triangle itself upwards, not downwards. Okay, so we could compute this. We could compute this directly, because this flow integral, this is the boundary, the integral around the boundary of this triangle of f dot dr. And we could do that, and it would be a good exercise. It's totally doable. But it would require three different integrals, right? Since this boundary is only piecewise smooth, we have to do the integral across each smooth piece separately. So we'd have to do three different line integrals. Let's see how it works out if we use Stokes' theorem, because Stokes' theorem says that this flow integral we're looking for is also the integral over the surface itself of the curl of f dot n d sigma. Okay, so let's work out this line integral. I guess to start with, let's find the curl of f. You never know what is going to happen if you find the curl of your vector field. So we need, let's see, I'm working out the cross product of del cross this vector field in my head. It's going to be, right, the derivative of, we need the derivative of p with respect to y, which is 0, minus the derivative of n with respect to z, which is going to be 4, comma, and then we need the derivative of m with respect to z minus derivative of p with respect to x. So m by z is 0, p by x is 6, and then n by x minus m by y. So that's going to be 0 minus 3, so plus 3. Okay. So minus 4, minus 6, plus 3. This is nice because this means our surface integral is going to be pretty straightforward, right? Because this vector field is actually a constant vector field. That's supposed to be a comma here. Okay, so to work out this surface integral, we still do need to write down a parameterization so that we can get the correct area element, because right, dx dy is not going to a patch of area here at above a certain xy value. Right, these patches of areas here and here are slightly different because the one on the triangle is at an angle. So to work that out, we need to parameterize. Well, one way to do it is parameterize this surface. Since it's a plane, right, we can see it contains the origin. If we go in the x direction, we can go any amount in the x direction and we end up on this plane. And that's the vector, right, the x direction is the vector 1, 0, 0. If we start at the origin and go out towards this point up here, let's see, if you look at this, let's see, this is 2, right, because x plus y equals 2, so when x is 0, y has to be 2. So this is 2, and that means this point right here is 0, 0, 2, 1, because z is half of y. Okay, but that means that this vector from the origin out to this point is also 0, 2, 1, just treating it like a vector. So any combination of these two vectors starting at the origin will put us on this plane. So we can just take the origin plus u times 1, 0, 0 plus v times 0, 2, 1. And then the partial derivative of r with respect to u is just going to be 1, 0, 0. Partial derivative of u r with respect to v is just going to be 0, 2, 1, and the cross product of these, RU cross RV, is, let's see, 0, comma, 1, minus 1, sorry, comma, 2. And notice that this is the upward pointing normal because our z coordinate is positive. So this is pointing in the direction we want. So now we can write down our surface integral. It's the integral, we'll come to the bounds in a second, but it's curl of f dot this cross product. So curl of f is minus 4 minus 6, 3 dot 0 minus 1, 2 d. Let's do dy dx. Okay, so now we need to write down bounds that will cover this triangle in the xy plane. I'm sorry. No. Right. U is x, but v is not y. So let's see. When u is 0 and v is 0, that puts us at the origin. This point right here, that's where u is 1 and v is 0. And this point right here, that's where u is 0 and v is 1. So it looks like, and everything is linear, so it looks like our u is going to go from 0 to 1, and then v is going to go, to go across this cross section, v has to go from 0 up to, I think, 1 minus u. Okay. All right. So now this cross, you can see that this integral is pretty straightforward, and there's only one of this integral. We don't have to do 3 different integrals like we did with the line integral approach. So this dot product is going to be, let's see, 0 plus 6 plus another 6, so 12 dv du. So integral from 0 to 1 of 12, so that's 12v from 0 to 1 minus u du. We can move that 12 outside. 12 times the integral from 0 to 1 of 1 minus u minus, and then when we plug in 0 we get 0, so just 1 minus u. So 12 times u minus 1/2 u squared from 0 to 1. So 12 times 1 minus 1/2, so 1/2, so 6. So we get 6. So this, was this easier than doing the 3 line integrals? Probably, I would say so. If this boundary was only one smooth piece, then probably maybe the line integral would have been easier. But I think for this particular example, because we would have had to do 3 different line integrals, I think the surface integral is a little easier. Also, it helps that the surface is just a portion of a plane, so that the parametrization was straightforward. And it also helps that the curl of the vector field was so nice, was a constant. Okay, let's look at another example. All right, so let's find the integral around this curve, the boundary of the portion of this plane in the first octant oriented counterclockwise from above. And f, our vector field, is this vector field. So always, you aren't usually obligated to ever use Stokes' theorem, but you always have to keep it in mind as an option, right? So for this, you always have to compare, would it be more work to do the line integral or the surface integral? For this one, the line integral looks messy because, the portion of the plane in this plane in the first octant, I mean, just figuring out, if we have, some plane sitting at an angle, we're going to be integrating over some angled triangle portion. Even just figuring out what are the boundary curves, that might take some work, right? And then we'd have 3 different integrals to evaluate. So to see if the surface integral seems better, let's evaluate curl. Let's figure out what curl of this vector field is to see if it will make the double integral nicer. Right? Definitely, as we saw in the last example, with a plane, our normal vector that we would use, right, this partial r partial u cross partial r partial v, for a plane, this comes out to be a constant. So that, right, that would be nice if we switch to the double integral. So let's see if curl is also nice. Right, partial p partial y is 0, minus partial n partial z, that's 0. And then for the y coordinate of curl, we get partial m partial z, that's 0, minus partial p partial x, that's 0. Things are looking pretty good. And then partial n partial x, that's 0, and then minus partial m partial y, that's 0. So actually, with the curl being 0, Stokes' theorem is a perfect shortcut, because now when we switch to the integral of curl over the surface that this bounds, we're integrating 0, and so we get 0. Right? So it always pays to just check what the curl of your vector field is, just to see if there's some nice simplifying that happens. This is kind of an extreme case where it simplifies all the way down to 0, but it's always good to know what the curl of the vector field is, because even if not all of the coordinates are 0, sometimes some nice things will happen. So it's always good to know what the curl is.